Okay, so here we are at the end of section 3, and we're going to look at our last chapter in this section, chapter 14, which is a look at powder metallurgy, or forming parts from powder. All right, so the powder metallurgy process is the manufacture of parts or products using very fine metal powders. Typically, this is going to be under pressure, so we're going to be applying some pressure, either a force from a compacting device or pressure from a gas or the surrounding environment. There may be heat involved in this, okay, but there is cold powder metallurgy as well as hot powder metallurgy. The powder metallurgy process has 4 basic steps. So the first step is we're going to make the powders, okay? The second step is we take those powders and we're going to blend them together. Now, in a typical kind of fashion, you're going to want to have some type of an alloy, or you may have some additional special powders in there. That's one of the benefits of the powder metallurgy process is the variety of recipes that you can make with your powder metallurgy process so that you can have specific customized parts. After you blend the powders, then you're going to compact it, okay? And that means we're making the shape that we want to make. So that compaction is going to be using pressure and or heat in some form or fashion. So we compact it into its shape. And then there's going to be a sintering process. Okay, so sintering is the term used to apply when we're adding heat to the what would be called the green part. Okay, so after we're compacting it, think of it as it has the final shape, but it is not held together very well. Okay, so it's not with its final strength or its final properties. So sintering is putting the green part, in an environment of an elevated temperature. And this is going to help to reduce porosities and kind of bring the part down to a better final physical or mechanical properties state. All right, so this is just the process again, but in more of a flowchart kind of layout, so it might be a little bit easier to understand what's going on. In the first step, we make the metal powders, and then there's some terms associated with this, or some different specific ways that we can make those metal powders. We're going to blend the metal powders together. Again, you know, this is to achieve the specific properties that we want with the part. In this process, we may be adding lubricants, because that's one of the benefits of the powder metallurgy process, is we can add things into the powder metallurgy process that aren't even metals. So we can add lubricants so that the final part has some type of lubricating properties. These lubricants can also be used to make the process of compaction more efficient. And then we can split into 2 different areas here. Okay, so after the powders are blended, we can either go to hot compaction. Okay, so we're using pressure and heat at this stage. All right, or we can do cold compaction. All right, and this is where we're just going to be putting the powders into the die or the mold, and then we're going to be applying a very high force to compact those together. All right. After cold compaction, there's going to be a sintering process. All right. Now, there's not sintering typically after the hot compaction, because the hot compaction is going to provide some type of sintering in the process. So you can almost view hot compaction as a combination of cold compaction and sintering. All right. Now, sintering is done at 80% of the melting temperature of the powder. All right. So we're not quite melting it, but we're getting it pretty close to the melting. All right. Notice that after the cold compaction, we have what's called the green part. Okay. So the part after cold compaction, like I said, is not going to be as robust as the final part needs to be. It's not going to be as strong. So think of compacting sand, right? So when we compact the sand together, there's still going to be a little bit or not a little bit, a lot of fragility with it. The sintering process is going to remove that fragility. So it's going to remove the porosities, and it's going to make it stronger, able to withstand the pressures and the forces that are required with the final part. And then whether you're doing cold compaction or hot compaction, there's typically a secondary and finishing operations that are done. All right, so this may be drilling holes, this may be finishing surfaces. Even though the surfaces on the part after the powder metallurgy process, whether it's cold or hot compaction, are relatively good, they might not be of the quality that you need for your finished part. All right, so that's a flow chart of the powder metallurgy process. This is another kind of diagram of the conventional powder metallurgy process, again, where we're going to be taking our base metals and powders and combining them, mixing them. Then we go through the pressing process, and we'll go more into detail on this in later slides. Okay, so the pressing. Then the green part is moved to the kind of like a conveyor belt here, where it's going to go through a series of ovens, stages where we delubricate it first. That is, we burn away the lubrication that we use to make the part. All right. Then we reduce any oxides, right? The rusting that happens. Remember, metals, anytime they're exposed to the air, are going to rust. So we need to reduce that. Then there's the sintering process, and then any heat treatment that is necessary, tempering, normalizing, things like that. And then the part is out. All right, so powder metallurgy process is a high volume production process, right? So we can make parts very quickly. We can make parts that are near net shape or net shape form. Now, you'll hear this term a lot, net shape or near net shape. What that means is that we're making the part as close to the finished shape as possible. Obviously, this is a very efficient production method. When we can make near net shape parts, it means that we only have a minimal amount of machining afterwards, finishing, drilling holes, things like that. In some cases with powder metallurgy, in some parts, we can make the finished part. That is to say, it's ready to be used after the powder metallurgy process is completed. All right. We can process difficult materials, right? Materials that are not able to be forged or cast. All right. So this is a great benefit for aerospace technology, some automotive technologies, special technologies. We can make custom alloys. There's very little waste. As with most forming processes, there is very little waste, but in powder metallurgy process, because we can reuse the powders that are not used in this, there's very little waste. And then we can control the porosity for porous metal parts. That is to say, if we want a metal part to have some kind of porosity in it, all right, so think when we might use this. So let's say we want to press in a bearing, right? So we want to press a metal into a shape for a bearing application. And we know that bearing, we need to lubricate it during its lifetime, during its operation, right? So we can press a metal shape for a bearing, right? But we can leave in porosities that then we can embed or impregnate with oil. So that now we have a metal part with oil impregnated into the porosity, into the holes of the part. And this is a great benefit because it improves the lifetime of the part. It extends the lifetime of the part, I should say. It also makes the part more efficient. So there's a lot of benefits to this. Here's a look at some powdered metals. Now, these powdered metals, one thing you should know about this, and you can see all the different ones. here. The powder metal is almost like a talcum powder. It's very, very fine powders. Okay. That means they're dangerous, right? You can breathe them in, and typically in a powder metallurgy process, you're going to be using ventilation equipment, very robust, very good ventilation equipment. You're going to have to wear certain types of breather or masking so that you don't breathe in this stuff. Some of the economics of powder metallurgy. I thought this was very interesting. Okay, so we have two examples here. So the example on the left, this is a machine part. All right, so this is just a gear, very straightforward spur gear, right? That is fully machined, and you can see we have the gear shape on the outside that is hobbed. Okay, so hobbed is a machining process. We'll talk about that later in the machining chapter. So basically, we're cutting the gear teeth here. We have a broached keyway, which means the keyway is just cut again, and then we have another hole that's probably drilled here. We have chamfers on it. This component cost ended up being very high with production rates that were very, very low. So you can imagine we have several different individual machining processes that are required on this. We can't do all this at once. So we have to cut the gear teeth, then we have to create the hole, then we have to broach the keyway, add the chamfers, all that stuff. So this was a very costly part. Now, the powder metallurgy part over here, this was created with a complete net shape without any machining operation. So this is actually the part that was produced through powder metallurgy. Notice the teeth were produced from powder metallurgy, as was the hole and the keyway. All right. So there was no additional machining operations. This cut the part cost by 40%. Okay. So that's a huge difference in this. All right. The part on the right was again a similar kind of situation. The existing part was entirely machined from bar stock, which means that we have a long, round, cylindrical bar. And we're going to cut off these discs and then do the machining process for this. So we have very low production rates with very high part costs. Now the powder metallurgy part on the right-hand side, the equivalent part offered a low component cost with quick delivery. So there was probably some machining that was needed to be done afterwards. Maybe we needed to finish the hole in here. But regardless to say, the part cost savings again was in the neighborhood of 38%. So the difference between a machine part and a powder metallurgy part, oftentimes we can get the final part using powder metallurgy. We have huge cost savings, 38, 40%. All right, so the economics are very, very well suited to powder metallurgy for many types of applications. Some of the benefits of powder metallurgy. So we mentioned some of these before, but we can process combinations of materials that would otherwise be impossible to mix. So these are friction materials, hard metals, or cemented carbides. You can see in here, these are cutting tools used in CNC applications. These are all powder metallurgy parts. All right. So diamond cutting tool material, electrical contact material, processing of materials with very high melting points, products with controlled levels of porosity. We already talked about this, where we don't want a fully dense part. We want the part to have some porosity or some holes into it so that we can impregnate it or reduce its weight or anything like that. And products with superior properties, such as magnetic materials, high-speed steels, and nickel and cobalt-based superalloys. All right, these are some of the unique benefits of powder metallurgy. Where do we see powder metallurgy? Well, primarily in the automotive industry. All right, and actually the two biggest markets are the automotive industry and the aerospace industry. In the automotive industry, 80% of all powder metallurgy parts are produced for the automotive industry. 75% of the parts on a transmission and an engine are produced from powder metallurgy. All right. And you can see I have a list here of the parts that are produced with powder metallurgy, you can read through those. If you're familiar with car engines, automotive parts, you probably have used, touched, felt, and maybe even repaired powder metallurgy parts. So the compacting process of the powder metallurgy process is where we're going to, is called pressing or briquetting. We can also produce it using an extrusion process, a rolling process, slip casting, centrifugal casting, that's tough to say, and high energy rate compacting. Now, some of these we've already talked about. Slip casting and centrifugal casting we talked about with the casting section 2, I believe. So the basic process for powder metallurgy looks something like this. Okay, so we have a die that's going to surround the whole process. We have a lower punch and an upper punch. All right, the part is going to be formed between the lower punch and the upper punch. So you can see the part here. And in this case, we're producing just a cylinder with a hole in it. Okay, then we have a core right through here. Now, it might be a little bit easier to see it in this diagram. So let me take you through the steps for this process. So the first thing is we have what's called a shoe, right? And that's the blue thing right here. Kind of looks like a shoe or maybe a golf club. And this is going to deliver the powder. So the shoe is going to slide over this hole and deliver a specific amount of powder. So the powder is going to drop into this area and it's going to fill that area. So to facilitate that, this bottom die is going to lower, all right? And the die is going to move down to accept a precise amount of the powder, all right? Then the shoe is going to retract, and the upper punch is going to come down and press, and the lower punch is also going to press up. So now we have pressing in two directions between the lower punch and the upper punch, and it's going to compact the part right there in the middle. All right. Then the lower punch is going to move further upward, raising the part up to the level of the surface, and then the upper punch is going to retract, and the shoe is going to move it off. So the shoe is going to push it off, and the whole process is going to repeat. All right. So the compression of the powder results in a green body. So this part right here, what's shown as part number 5, this is our green part. All right. So the green part, again, means that it hasn't been sintered. It still is in a fragile state. It's not ready to be used. All right. And it's going to go on to the sintering or heating stage so that it can achieve its final material and mechanical properties. An extrusion process is kind of a similar kind of process that we have with compacting, but the compacting is going to be done with a kind of a tapered wheel. So this wheel is going to be constantly rotating. The wheel is tapered so that on the side where the extrusion is going to happen, so the powder is going to be moved out through this area, extruded. That's where the tapering occurs. So the tapered wheel is going to force out the powder. The powder comes in here, and the powder is going to be pressed and pressed down along here until finally it's going to be squeezed out and extruded into a uniform shape. So isostatic forming is when we're using a gas all around, a high pressure gas all around the part to form it into shape. That's what isostatic means. Isostatic basically means that the static pressure is going to be formed all around the part. Okay, so from all directions. So the part is going to be placed into this chamber, and then the in some cases the heated gas or just the high pressure gas is going to be inserted into that, and it's going to press on all surfaces so that it's going to get that compaction. But you can compact more complex shapes here, and you can get into the nooks and crannies, so to speak, control the porosity again through the hot isostatic pressing, which is also known as the HIP process, hot isostatic, HIP, the hipping process, or cold isostatic pressing. Sintering is what we do to the green part after we finish compaction. Okay, so after compaction, whether it's, whatever type of compaction we're doing, the part is called the green part. And in order to get it to its final state where we can use it, we have to take the green part and we have to sinter it. And sintering heats the green part to 60 to 80% of the melting point of the principal powder. All right. So sintering is going to bond the atoms of the metal together, increasing the density, improving mechanical properties. So you can see the stages here. This is the loose powder. All right. Then the initial stage, intermediate stage, and then the final stage of the sintering process. All right. Now, in this, it's important to understand we're not melting the part again. We're not melting the powders. Obviously, that would destroy the geometry of the part. We're just heating it up to 60 to 80% of the melting point. So we can control porosity here. And in this diagram, I like this because you can still see some of the porosity in here. All right. But, it's much higher density than any of the other previous stages. Some ideas for the sintering temperatures. And obviously these are very loose. You need to look at the specific properties of the powder, the specific recipe of the powder that you're going to be using. But just to give you an idea, iron and steel in the neighborhood of the low 2000 degrees Fahrenheit, aluminum a little bit above 1000 degrees Fahrenheit, copper 14 to 1800, brass a little bit higher, 1550 to 1750 degrees Fahrenheit, bronze in that same neighborhood. And then the hard metals, this would be Inconel, nickel, any of your special aerospace metals. Aerospace, I say aerospace because these are often metals that are used in the engines in jet engines, where we have extremely high temperatures to deal with. So only special metals can be used. In those rocket engines is another application of powder metallurgy. So here the melting temperature is very high, upwards of near 3000 degrees Fahrenheit. And then finally, just a brief talk about some of the secondary processes. Keep in mind that we'll talk about some of these secondary processes in later chapters, but some of the secondary processes that are common for powder metallurgy part includes infiltration. All right, this is where we are introducing other metals into the green part. Okay, so think of the green part having the enlarged porosities, right, in it. So the green part still has those voids in it. And we can actually put lower melting point metals into those porosities. So we can melt the, let's say, copper, right? Because copper has a very low melting point compared to some other metals. So we can melt the copper and allow it to infiltrate into the metal part, the green part. This is going to increase the part density, right? Because we're introducing a metal in there. It's going to fill in the porosity, the voids. It's going to increase the hardness and strength, but it's also going to provide a unique metal properties, right? Impregnating, I also talked about this. Impregnating is where we introduce oil or other lubricants into the porous bronze or iron bearings, okay? And then sizing and coining operations. All right. These are cold form pressing operations, where we can just kind of stamp out, parts cold forming. This increases the density and dimensional accuracy of the part. All right. So that finishes powder metallurgy. That also finishes section 3. All right. So, remember to watch the videos, right? I have lots of videos in the Canvas, in the Canvas module, in this Canvas module for powder metallurgy and the other forming processes. Please watch those videos. It will paint a much clearer picture. And, I kind of recommend that you watch the videos while you're going through the PowerPoint. I think that's a good way to go through things. I've kind of labeled the videos so that at the different stages or different topics in the PowerPoint, you'll be able to find videos that correspond with that. I think that's very helpful to kind of paint that clear picture. But regardless, please watch the videos. And I will talk to you in section 4. All right.